Hello students, this is the video going through the Trig and Rational Functions Bootcamp. The big idea here is really to get us comfortable with doing stuff like finding sine of pi over 6, and to a lesser extent solving trig equations, and then reminding us how to reduce rational things. So the big idea is really going to be focusing on understanding those unit circle values. Trig is not a huge part of what we're doing in calc, but it is going to be present in almost every piece that we do this year at small levels. All right, so first things up, we've got to work with unit circle trig values. And the big idea is being able to, one, identify what type of reference triangle we're dealing with, to two, figure out what quadrant we're looking at, and three, to actually get the value. Dealing with sine of pi over 6, that's going to be in the pi over 6 family. In fact, that's going to be our reference triangle. Pi over 6 is 1/2 and root 3 over 2. Sine is going to be our opposite over hypotenuse. You might also think about this as our y coordinate, where here we have root 3 over 2 and 1/2. And because we are in the first quadrant, where we're going from 0 to pi over 2, we have a positive value here. So the answer to this is 1/2. For our second one, we're looking at the pi over 4 family. And that's going to be root 2 over 2, root 2 over 2, and 1. If we think about this, I'm just going to draw the first quadrant down here because that's going to make our lives a little bit easier. We've got pi over 6 at root 3 over 2, comma 1/2. We've got pi over 4 at root 2 over 2, root 2 over 2. And we've got pi over 3 at 1/2, comma root 3 over 2 rather. We also have our stupidly named quadrantal points at 0, which has the coordinates 1, 0, and at pi over 2, which has the coordinates 0 and 1. Okay, cosine is going to be our x value. So that's value of the square root of 2 over 2. For sine of 2 pi, that is one of our quadrantal angles. We know that goes all the way around. And here we'd have the point at 1, comma 0. Sine is our y value, so sine of 2 pi has a value of 0. For tangent of pi, that's another quadrantal angle. That's going to be here at -1 and 0. Tangent is the y coordinate divided by the x coordinate, so that'd be 0 divided by 1, and that gives us 0 as an answer. For secant of pi over 2, that's the same thing as the reciprocal of cosine of pi over 2, and I often find that a little bit easier for us to work with. So looking at this, we've got 0, 1, and cosine there would be just the x-coordinate. 1 over 0 is undefined for our secant value. For cosine of pi over 6, we already got the triangle for pi over 6, but now we're looking at the x value instead. Pi over 6 is going to be in our first quadrant. And when we do that, we end up getting a value of root 3 over 2 for our x. For sine of pi over 3, we're in our first quadrant again. Now we're looking at the upper value, so that's going to be at 1/2 root 3 over 2. Sine is the y value, so that's root 3 over 2. For sine of 3 pi over 2, that's another quadrantal angle. Here we've got 0, -1. Sine is the y value, so that's going to be -1. For tangent of pi over 4, we're in our first quadrant, and that's the one that we have root 2 over 2 and root 2 over 2, because all pi over 4 family angles will have that. Tangent is the y divided by the x. Since those are the same value, when we divide those, we get 1 as an answer. For cosecant, that's the reciprocal of sine, and we're talking about a quadrantal angle again, so we're going to take a look at the top. We got 0, 1 up there. Sine is the y value. The reciprocal of 1 is just 1. For sine of pi, that's over here at -1, 0. The y value there would be 0. And for cosine of pi over 3, we just saw this angle with sine for number 37. Here we're looking for the x value instead of the y value. So that's 1/2 instead of the √3 over 2. There are lots more of these to practice. In fact, there are an infinite number in the delta math thing that I set up for you so that you can practice these as many times as you need to begin to feel comfortable with them. This is probably the most useful set of things for you to be able to do for trig things. As we move a little bit forward in this, we're going to have to deal with things that are outside of the first quadrant and quadrantals as well. Looking at some trig equations, here we're trying to find angles where these things are true. So if we're talking about sine is equal to 1/2, we can think about this in two different ways. One is in terms of just our circle, and here we get positive value, and sine is, or y equals 1/2. That's going to happen at either of our 2 pi over 6 angles. These are the lowest ones on each part of this. So that would be at pi over 6 and at 5 pi over 6. As an alternative, if you think about a triangle that would end up with opposite over hypotenuse equal to 1/2, that only happens in a 30, 60, 90 triangle. That means that we'd end up with √3 as our long side, and we'd have 30 degrees or pi over 6 as our angle. That's why we use that triangle as our reference triangle there. For tangent is equal to 0, that's in terms of our unit circle. We're looking for places where y over x is equal to 0. This only happens when y is equal to 0, so we're talking about these 2 points. We've got both ends included, so x could be 0, that's there. X could be pi, that's here, and x could be 2 pi, back to the beginning again. For where cosine of x is equal to -1, we're looking for places on our unit circle where x is -1. And if I think about that, that only happens at our leftmost point, which is at -1, 0. So in this case, x is equal to pi. Here we've got a review of just kind of dealing with our 6 trig functions, sine, cosine, tangent, as well as secant, cosecant, and cotangent. Looking at the stuff that we have here, we should know that based on the angle theta, and I can't quite see, so I'm going to move this a little bit. So we've got sine of theta is opposite over hypotenuse, like I touched A as I said hypotenuse, so that would be B over C. Cosine is adjacent over hypotenuse, that'd be A over C, and tangent is opposite over adjacent, so B over A. Cosecant is the reciprocal of sine, so that would be C over B. Secant is the reciprocal of cosine, so that would be C over A. And cotangent is the reciprocal of tangent, so that would be A over B. To quickly go through this part, I'm only going to find the original one instead of all 6. I'll leave that for you. So secant is the reciprocal of cosine. Cosine would be 11 over 14. Sorry, I assume the angle is down here. Cosine would be 5√3 over 14. So secant of theta would be 14 over 5√3. Number 2, tangent. We're talking about opposite over adjacent. That'd be 5/12. Number 3 is tangent again, and that would be opposite over adjacent, 3√17 over 4. Number 4 is sine. So here we're talking about opposite over hypotenuse. And when we do that, we get 15 over 25. For number 5, we got tangent again. That's going to be opposite over adjacent. That would end up being 8 over 12. For number 6, we're talking about cosine. That would be adjacent over hypotenuse. So that'd be 15 over 17. For the next page, we've got to find the exact trig values of each of these functions. This is similar to what we're doing on the first page, and it's going to be based on the coordinates and our reference triangles that we've got going on here. So at this place, we've had the point 0, 1. Cosine is the x value, so cosine of pi over 2 is going to be 0. For cotangent, that's the reciprocal of tangent. And if I know that tangent is y over x, we've got to flip this to become x over y. So we're looking for our x over y here. And for a pi over 4, this is going to be one of the root 2 over 2 ones. And since I know this is in the second quadrant, that means my x is negative. If I divide those two things, since they're the same but opposite signs, we get -1 as our answer. For secant of theta, that we're looking at 11 pi over 6. First thing we need to know is that secant is the reciprocal of cosine of theta. So whatever we get for cosine, we're then going to flip. For a pi over 6, we've got root 3 over 2 and 1/2 as our values. In the fourth quadrant, our y is negative. Cosine is our x value, so we're going to take root 3 over 2 and we're going to flip it, giving us 2 over the square root of 3. For our last one, we've got sine of theta given pi over 2. And we got the coordinates 0, 1. Sine is our y value, so therefore our value is 1. Here we've got a whole bunch more of unit circle values. We know secant is going to be related to cosine. Cosine of, I'm just going to draw one of these, I think, and make my first quadrant really big. So pi over 6 is going to be root 3 over 2, comma 1/2. And for cosine, that's the x value, and we got to flip it to get 2 over the square root of 3. For number 14, cotangent is related to tangent. And for 5 pi over 3, well, that's in the pi over 3 family. Root 3 over 2 is our y, and 1/2 is our x. And if we're talking about this in terms of 5 pi over 3, that ends up being down in our fourth quadrant. So for this, our points would end up being 1/2 comma negative root 3 over 2. Looking at this, tangent would be y over x, so I want to flip these and do x over y. That'd be 1/2 divided by negative root 3 over 2, which is the same as 1/2 times 2 over negative root 3. That gives us 1 over negative root 3. For number 15, we've got cosine of pi over 4. That's going to be our pi over 4 family, so root 2 over 2. And root 2 over 2, that is in our first quadrant. So that is going to be just root 2 over 2. Cosine of pi, that's one of our quadrantals. That's going to be at -1, 0. The x value there is -1. For cosine of pi over 6, we already have that value. We're looking for the x, and that's going to be root 3 over 2. For secant of 5 pi over 4, secant is the reciprocal of cosine. So I'm going to find where that is. That's going to be down here in our third quadrant. So our points would be root 2 over 2, comma root 2 over 2, but both negative. And for cosine, I want the x, so I'm going to flip that upside down and get -2 over root 2. For cosine of 4 pi over 3, that's going to be based on our pi over 3 family, and that's going to end up in the third quadrant as well. That would give us values of 1/2 and root 3 over 2. Both of those negative for being in the third quadrant. And cosine is our x value, so that would end up being -1/2. For cotangent 11 pi over 6, that's going to be down here. That's based on tangent, so I'm going to use my root 3 over 2, comma 1/2. Since we're in the fourth quadrant, then 1/2 becomes negative. And cotangent is going to be the reciprocal, so x over y. When I divide these two, we end up getting negative root 3 as our answer. For tangent of 3 pi over 2, that's going to be at 0, -1, and y divided by x would be -1 over 0, which is undefined. And for cosine of 7 pi over 6, that's going to be in the third quadrant, and it's going to be based on the x value of our pi over 6. Third quadrant, that would be negative, so that's root 3 over 2. We've got a whole mess of other problems for this. We've got another 10 on this page, another 10 on the page after that, and another 10 beyond that. Following that, we have the solutions to all of these so that you can check those. I will not go through those other 30 problems because it's the same process for each of those things. Then we get into solving equations. So the trick here is we got to get the trig thing by itself. Sometimes that's going to involve doing some other things, but otherwise we're just getting that trig part by itself first. So what I might do here is take a look at this and move my -2 sine theta onto the other side. That gives me -3 sine theta plus 2 root 3 sine theta cos theta. And at this point, I can factor a sine theta out of this because that's going to equal 0. So when we do that, we end up with -3 plus 2 root 3 cosine of theta. That gives me two options. The first is that sine theta equals 0. That happens at any time that our y value is 0 for our unit circle. So those are these 2 points. So that means theta could be 0 or pi. It can't be 2 pi because this is a non-inclusive endpoint for our domain. For the other part of this equation, that's -3 plus 2 root 3 cosine theta is equal to 0. Getting the cosine theta by itself, we end up with -3 over 2 root 3, which ends up being bigger than 1, and there's no value that we have, less than -1. And there's no value of cosine that exists for that to work that way. For number 54, I'm going to bring everything to one side, and when I add 3 secant theta to both sides, those cancel out. Then I'm going to factor a sine out of both of these, so sine theta, then 1 plus secant of theta, and that's equal to 0. We get sine theta is equal to 0, which we just had in the previous problem. That gave us 0 and pi. And if we have 1 plus secant theta is equal to 0, that gives us secant theta is equal to -1. What that really means is that the reciprocal of this, cosine theta, is equal to the reciprocal of -1, which happens to be -1. This happens when we have the point -1, 0, and gives us another answer that's equal to pi. For the third one, I'm going to bring everything to the same side again. I'm going to bring the squared part to the left so that we have everything. The squared term is positive, and order these in terms of a quadratic. So 2 cosine squared theta plus 3 cosine theta plus 1 is equal to 0. Factoring that, that's going to give me a 2 cosine theta and a 1 cosine theta. I've got a +1 and a +1, and just to check, 1 times 2 would give me 2, plus 1 more would give me 3. Okay. If we got 2 cosine theta is equal to -1 from that first parentheses, that gives us cosine of theta is equal to -1/2. That happens when we have x values of -1/2, which are going to be at the pi over 3 angles, but the 2 in the left side of our coordinate plane. So we're looking at 2 pi over 3 and 4 pi over 3. For cosine of theta plus 1, that gives us a cosine value of -1. We talked about that in the last problem, where that is a value of pi. For the next one, I'm running out of room here, so I'm going to try to fit this in, but I'm not sure that I can. I'm going to bring everything to one side again. Cosecant of theta plus cosecant of theta cosine theta is equal to 0. Factor out a cosecant theta, and we end up with 1 plus cosine theta is equal to 0. Cosecant theta equals 0. That one's the reciprocal of sine, so that would mean that sine theta is 1 over 0, and that doesn't make sense, so there are no solutions for that side. For the other one, we got 1 plus cosine is equal to 0, which means cosine of theta. -1 is equal to cosine of theta, and we keep seeing this come up again and again. That's the one that gives us pi as our value, because that's where our x-coordinate is -1. We've got a whole bunch more of these to solve. These are doing exactly the same thing. You're probably going to bring everything to one side, factor if need be, and then solve each of those pieces, looking for values that make that true. These are the solutions to those problems. In the next part, we're now moving on to irrational functions. And at first, we're really going to be talking about all the different parts of this that are important for us. The goal here is really to talk about asymptotes, to talk about what causes things to be wholes, and to talk about factoring some more. So when I look at this, first thing I'm going to do is to do some factoring, and I'm going to rewrite this as 1 over, and I'm going to take a negative 3 out and get x minus 2. The reason I'm going to do that is that then I know that if x minus 2 is equal to 0, we have a divide by 0 situation. This is going to cause a vertical asymptote because it doesn't cancel out. So that's going to be at x equals 2. So when I draw that asymptote in, we have the start of this. The second part about this is dealing with a horizontal asymptote, and that's what happens when we plug in really big numbers. And in this case, if I plug in really big numbers like 1 billion, we have basically 1 over negative 3 billion, which is essentially 0. Horizontal asymptotes really should be called end behavior asymptotes because they're all about what happens when we get to really big numbers. We don't have any holes here. Holes happen when we do some canceling, and I'm not really concerned about the intercepts right now. So my overall graph for this is going to look something like this, although again, I don't really care so much about that. I'm much more interested in the asymptotes for the purposes of calculus. Looking at a couple more of these, in fact, I'm just going to look at number 65 because all the rest of these have answers there. I'm going to do some factoring because we're going to talk about a hole with this one. We got x times x minus 2. And then we've got x times x plus 1 on the bottom. A couple of things are going to happen here. First, I know that x cannot be 0 and x cannot be negative 1 based on that making the bottom 0. But then, when I cancel out those x's, we have a different function going on. We have a function that would have a horizontal asymptote at 1 because my leading coefficients for same degree top and bottom are going to divide to 1. And we have a vertical asymptote at negative 1 based on the remaining piece there. However, we're basing our graph off of our original equation, which means we can't use 0 either. So 0 is going to be a hole. So x equals 0 is going to have a hole. And if I plug 0 in, that would be at negative 2 over 1, so negative 2. We have a hole at 0, negative 2. That also gives us a pretty good idea of the shape of this graph. It's going to look something like this and mirrored on the opposite corner. Looking at this, we have some more problems for us to graph, and then we have the solutions to those. The ones at the end are going to be much more important for what we're doing, and these are all going to be based on factoring and reducing. Stating the excluding values is based on whatever values will give us 0 in the denominator. So again, this is more practice factoring. Whenever we are dealing with these, we've got to factor and then state our excluded values and then reduce. The answers for these are not at the end of this, but I'm going to trust on your ability to factor to kind of get through this. And for the last couple, we have to think about vertical asymptotes. So vertical asymptotes at x equals 4 means that the bottom would be 0 when x equals 4, and that part doesn't cancel out. For number 18, we're looking for which of these statements is true. These are vertical asymptote, horizontal asymptote. It's going to be based on when you factor this. If things cancel out, they turn to holes. If they don't cancel out in the denominator, they make an asymptote. And horizontal asymptotes happen based on if you plug a really large number in. For these, I think, are at the end. And then finally, we've got some domain and range stuff going on here, and then asking about horizontal and vertical asymptotes. The domain for these is going to be based on the vertical asymptotes. For example, number 14 starts at negative infinity and goes up until negative 1. I'm going to use interval notation for this. We don't actually get to negative 1, so we're going to use a parentheses instead of a bracket. We use the union symbol to make our next set of domain. That's going to go from negative 1 to positive 1. And then I'm going to do another union symbol, and that's going to go from 1 to infinity. Similarly, the range, we've got one part, which is going from 3 up to infinity. And it looks like the other part is stopping at 2. So I'm going to use a square bracket for that and go to negative infinity.